Hello deep learners, welcome to this third lecture of PyTorch 0 to Hero playlist where we are going to learn about what are gradients, what is the typical process of building and training a neural network looks like, what is Autograd, and lastly we are going to see how we can use this Autograd to improve our training and make it faster. And lastly also we are going to see how to clear gradients inside Autograd. So the last concept is a bit advanced one, but it will be very clear throughout the video. So we'll learn everything in this lecture. So take a pen and paper, grab a hot cup of coffee, and let's get started. Alright guys, so before jumping into Autograd, I want to first make your concept of gradients much clearer. Because if you don't understand the idea of gradients, then Autograd will be simply a black box for you and you won't be able to understand it properly. So first, let's revise the concept of gradients. So simply, suppose we have a function which takes some inputs and gives us an output, right? So that's a simple function. Now, this gradient tells us that if we change our inputs, then how much will our outputs change? So simply you can think of gradients as the rate of measure which says us that how much will there be a change in our output if there's a change in my input. So in a way it tells us how our inputs are influencing our output. Alright, so you can think of gradients like this. So let's say we have y equals to f of x. So this y is my output and this x is my input. So you can think of it as, suppose this is my x1, this is my x2, this is my x3, this is my x4. So combined, this is my x or my input. Now I pass this to a function. So let's say this is my function, so this is my f function and it takes these inputs, so these are my inputs. So it takes these inputs and it gives my output which is y. So this is my output, right? So that is the simple concept of a function. Now suppose my x1 is x1, x2, x3 and x4. Let me say my x1 is 1. This is 2, this is 1 and this is 5. Now let's say I pass this to my f function and I got my y as, let's say 10. So this is my case 1. Now in the second case, let me say that I changed my x1 to 5. Okay, and I changed my x2 to 3. And my remaining x3 and x4 are the same. Now as you can see, there is a change in my x, or there is a change in my input, right? Why? Because my x1 changed. Earlier it was 1, now it is 5. And also my x2 changed. Earlier it was 2, now it's 3. Now let's say if I pass this to my f function and let me say I got my y as 5. So as you can see, when I changed my input, my outputs also changed, right? So this is what happens when we change our inputs. Our outputs also change. Now, what gradients do is, let me say this is y and these are combined x, okay? Now what this gradient calculates is how much will y change if x changes. So it just measures and says us that if I change my x, how much will my y change, right? So it is used to find this relationship, and that is why gradient is so much important. So let me say I want the gradient to understand how much will my y change when there is a change in my x. then the gradient will look like dy by dx simply, right? So it tells us that if there is a change in my x or my input, how much will my y or my output change? And that is the whole concept of my gradient. Alright, so I hope that you guys understood the concept of gradient. Now let me say I have an equation which is y is equals to 3x square. Alright, so let me say my input is x and my output is y. Alright, so how to calculate dy by dx? So I assume that you all know these things, but again I'm just giving a revision. So simply dy by dx will be nothing but it will be, first this is my constant, so this will 3 will come out, and then the derivative of x square is nothing but 2x, right? So it's 2x and I got 6x. And how did I came up with this? So simply this is the formula. The derivative of x to the power n is nothing but n times x to the power n minus 1, right? So that is what I put here. I got 2x and this is my final output. Simple. Okay, now let me say the equation changed. So let me say y is equals to sine of 10x square. Alright, and my z is 10y. Now I want to measure dz by dx. Now what is dz by dx? So dz by dx is nothing but it tells us how much my z change if my x change. So how much will my z change if my x changes, right? And that is what my dz by dx is. So let us solve this. So I hope you all know the chain rule. So dz by dx will be nothing but dz by dy, because z is dependent on y, times dy by dx, because y is dependent on x. And what is this? This is my chain rule applied. Alright, now let's solve this. So dz by dy, so if we expand this, it will look like this, and if we expand dy by dx, it will look like this. Now this will be nothing but 10, because it's a constant and it will come out, and dy by dy is equals to 1. So this is the first formula we use. This is the second formula we are using. And next, the derivative of this. So sine of, you can consider it as x. So sine of x will be cos of 10x square. Then applying chain rule, we get this. So it will be nothing but 20x cos of 10x square. And combining this and this, we get the final output as 200x cos of 10x square. And lastly, let's consider another sum. So let's say the sum is this: y is equals to x square plus 1, and my z is 3y square, and my u is sine z. Now let me say I need to find my du by dx. So first understand what this gradient tells us. So this gradient tells us how much will this change, or how much will my u change if my this changes. So if my x change. Simple. Now how to solve this? So using the chain rule, you can easily expand it and get it like du by dz times dz by dy times dy by dx. Now expanding this, we will get sin z, and sin z will be nothing but cos z. So this is this. Now dz by dy will be nothing but, let me write it again, so it's 3y square, and this will be dy by dx will be nothing but dy by dx of x square plus 1, right? Now let me expand this, so this will be nothing but 6y, and this will be simply, if you expand this, this will become dy by dx of x square plus dy by dx of 1. This will be 0, this will be 2x, right? So you can see we got cos z times our 6y, so this is cos z, this is 6y, and we got 2x, right? Simple. And if we expand this, we'll get 12xy cos z. It's again simple. Now if you put everything in terms of x, you'll get, so y is x square plus 1, so x square plus 1, and cos z, my z is 3y square, and if I put the value of this over here, it will again become x square plus 1 square. And this is what the equation will look like. So the final answer is nothing but my 12 times of x square plus 1 and cos of 3x square plus 1 square, right? And this is my du by dx. Alright, so once we have solved this, let us code it. Let us code these three equations so that we understand how to manually code these gradients, and that will basically make our understanding of Autograd much easier. So let us first code it. Alright guys, so this is what the code of the three equations that we computed looks like. So at first we have to import the packages, the math and torch packages. Yeah, so once it got imported, let us see the first problem. So this was the first problem, which was y equals to 3x square, and we had to find the derivative of y with respect to x, right? So we computed it and we got 6x. So that is what we are returning as the output from this derivative function. So it takes my x and it returns 6x, and that is what we calculated also. So this is the function. Now I just passed a random x as 5, so it will give us 30, which makes very sense. Alright, now the next problem was y equals to sine of 10x square and z is equals to 10y. So we had to find the derivative of z with respect to x, which tells us how much will our z change when we change our x or our input. So for that again we have coded this function dz by dx, which takes an x and it returns this, which we also calculated. So it returned 200 times x times cos of 10 times x square. So that is what it's returning. Now again I inputted a random x as 5 and it gave me the output as 240. Okay, and this was the third problem where we had three equations. So y is equals to x square plus 1, z is equals to 3y square, and u is equals to sin z. And we had to compute derivative of u with respect to x. And what does it tell us? Simply it tells us how much my u will change when I am changing my x. So again we created this function which takes x and returns this, and this is what we actually calculated also. Now I just invoked this function and passed a random x as 5, and we got the input as 158.75. So that is what the code of these three equations looks like. Alright guys, so now that we have an understanding of what gradients are, let us see how gradients play an important role in the process of backpropagation. So let's see what is this backpropagation algorithm, and I'll cover it in within 5 minutes. Alright, so what is this backpropagation? This backpropagation algorithm is nothing but this is the idea of training our neural network. So what happens is, let's say this is my neural network and this has millions and trillions of parameters. And what are these parameters? These are nothing but weights and biases. So our neural network has these weights and biases, and together they form this neural network. Alright, now let's say my X is my input, my Y is my output, and this is my actual output, and my Y hat is my predicted output. So this is what is this predicted output? Let's see. So first what happens is, this is the first step. So what happens in this backpropagation algorithm is that we have our X, which is my input. We pass this to our neural network. This one. We pass this to our neural network and we get the Y hat. And this Y hat is my predicted output, or the output which my neural network has predicted for this input. Alright. So now once that we have got this Y hat or this prediction output, what we do is we calculate loss. So we calculate loss between what? We calculate loss between my Y hat and my Y. Alright. Now what is this Y hat? It is my predicted output. And what is this Y? This is my actual output. Now that we have calculated this loss, it tells us how wrong our predictions are. It tells us how wrong our model's predictions are. Right. So next what we do is that we compute the gradients of loss of this L with respect to all the parameters in the neural network. Okay, so what does it mean? So it means that once we have got our loss, we now compute the gradient of our loss with respect to all the parameters in the neural network. So simply we calculate this. Alright, now what is this? So let me say my W represents all the weights in my neural network, and my small b, it represents all my biases in the neural network. Alright, then we basically compute this. What is this? This is the gradient of loss with respect to W, which is all my weights in the neural network. And what is this? This is my gradient of loss with respect to B. And what is B? All my biases in the neural network. Right? So we compute this, and what does it tell us? This tells us how our loss will change when we change our W, and this tells us how our loss will change when we change our biases. Right? Simple. Alright. Now that we have computed these, we go to the fourth step, which is updating the parameters, and we do that using gradient descent. So what does this gradient descent algorithm says is that once we have computed these, we basically update our weights of all the neural networks. So Wn, let me say this is my new weights, is equals to W old, which is these weights, minus eta times del L by this. Right, so what is this? Alright, so you can all ignore this N and O. So simply it is this equation. So weight is equals to weight minus eta, what is this? this is my learning rate, which is a hyperparameter which we set, times this, which is this, the gradient of loss with respect to all the weights in the neural network, right? And similarly, we update our biases using the same formula. So B is equals to B minus eta, this is eta, this is eta, this is eta, this is not N, times del L by del B. So here we are using this, which is the gradient of loss with respect to all the biases in the neural network. And this is how we update our parameters. And the idea is that we update our parameters in our training process and we go on doing it until and unless our y hat, it tends to our y. Meaning that my y hat on a predicted output is as correct as my actual output. Okay, so due to it, my loss will get minimized, right? Because this loss calculates how wrong our predictions are. So the more this y hat becomes like y, or the predicted output becomes like my corrected output, obviously this loss will get minimized. And that is what is the whole idea of our gradient descent and my backpropagation. So we go on training it until and unless we find such optimal values of weight and biases for which our neural network is producing such output which is very close to our actual output. And due to it, we are minimizing our loss. And that is the whole idea of backpropagation. And that is why these gradients are so much important. Because without this gradient descent logic will basically fail, right? Because if you don't compute this, then how come they will come over here? So that's why gradients, they play a very important role in backpropagation and in the training of neural network. So guys, that's why we can say that gradients are the only reason why a neural network can learn. Because it tells us exactly how each of our parameter or each of our W and B, it contributes to this loss. And without it, we can never update our parameters in a way that we converge to a minimal loss and we get correct model predictions. So you can say that gradients only give the power to our neural network to actually learn and get smarter during this training process. Otherwise, it wasn't possible. Alright guys, so now that we have understood the role of gradients in backpropagation, let us understand backpropagation much deeper. Alright, so let's say that we are working on the problem of binary classification. Alright, so this is the problem that we are working on, and we have our neural network, which is nothing but we know that it is the combination of all the weights and biases, right? And we have our x, which is our input, we have our y, which is the actual output, and we have our y hat, which is nothing but the predicted output, which our neural network is predicting. Alright, and we have our loss function as our BC. What is this? This is my binary cross entropy, which is used in binary classification problems. Alright, so this is how the whole process works. So at the very first, we do forward pass. Okay, in this forward pass, two things happen. So what actually happens is, this is my x, which is my input. I pass this to my neural network and I get my y hat, which is my predicted output. But here two things happen. First is that my z is calculated, which is nothing but w times x plus b. So this w is nothing but all the weights in my neural network, and this x is my input, and this b is all my biases in my neural network. So first we calculate this, and then we calculate our y hat as sigmoid of z. So what is this? So this is basically sigmoid, and this is nothing but this is an activation function. This is sigmoid which is again used in typical binary classification problems. Alright, so we pass our z to this sigmoid function and we get our y hat. And the formula of sigmoid function is simple. It is basically this: 1 by 1 plus e to the power of minus z. And what my sigmoid does is, it takes my z and it squeezes it to a range of 0 to 1. So it is any floating number between 0 to 1, and suppose it is 0 to 0.5, we consider it as 0, and if it's 0.5 to 1, we consider it as 1 in typical binary classification problems. Alright, so this is the first step. The next step is loss calculation. So what do we do here? We basically calculate our loss by passing y hat and y, which is my predicted output, and my actual output to BC. Why BC? Because BC is my loss function. So by this function, it takes my y hat and my y and it returns a number. And what is loss? It's basically a measure of how wrong our predictions are, or in this case our y hats are. Alright, and now what is this BC? So this BC's formula is minus of y log of y hat minus 1 minus y log of 1 minus y hat. So this is the formula of my BC. And now once that we have calculated our loss, we calculate the gradients of del L by del W and del L by del B. What is this? It is the gradient of loss with respect to all the weights in the neural network, and this is the gradient of loss with respect to all the biases in the neural network. So this tells us how our loss changes on changing our weight. This tells us how our loss changes on changing our biases. Alright, now let's apply the chain rule. Okay, so applying chain rule, you can see that my loss is a function that is dependent on y hat. So I can write it like this, right? Times, now this y hat is a function of z, right? It's a function of z. So del of y hat by del of z. And lastly, this z is a function of my w. So basically it's del z by del w. Similarly, my del L by del B is nothing but del L by del y hat times del y hat by del z, that's a del y hat by del z times my del z by del b. So we had to compute this. So we applied the chain rule and we got these equations. This is 1 and this is 2. So basically we have all this and we have to compute these gradients in the third step, right? So this is my third step. So how does it work? So you can see that this gradient, this gradient and this gradient is same. This gradient and this gradient is same, and these are different, right? These two are different. So basically we have to calculate 1, 2, 3, 4. So we have to calculate 4 gradients. Alright. Now let's first calculate this one, which is nothing but del L by del y hat. So if you see carefully, my L is this whole equation, and I have to find the derivative of this equation with respect to y hat. So first let me consider this term. So minus y will come out and derivative of log of y hat will be nothing but 1 by y hat. So I can write it like this, and this is again I am considering it as another term. So first this will come out because it's a constant, and then the derivative of this will be this, and then applying the chain rule will get as minus 1 over here. So this is nothing but minus y by y hat. This minus and this minus will get multiplied and become plus, and it's 1 minus y divided by 1 minus y hat. Now let's expand it. So we are considering, so on expanding it, we get it as minus y times 1 minus y hat plus y hat times 1 minus y. And if we further do the plus minus, we'll get as minus y plus of this and plus of y hat minus of y hat y, and bottom it's y hat 1 minus y hat. So basically what we got is this and this will get cancelled, and what we got is y hat minus y divided by y hat 1 minus y. So this is what we got, y hat minus y, and in the denominator we got y hat 1 minus y hat. Right. So what is this? This is my derivative of loss with respect to my y hat. So we calculated this one. Now let's compute this one. So derivative of y hat with respect to z. This is nothing but it's the derivative of sigmoid of z with respect to z. And the derivative of sigmoid, it's very simple. It's sigmoid 1 minus sigmoid, right? So this is the general formula. And if you further put y hat in place of my sigmoid of z, we'll get y hat 1 minus y hat. So what is this? This is my derivative of y hat with respect to z. So we also calculated this. Now lastly we have to calculate this and this. The derivative of z with respect to w is nothing but it's x, right? And similarly the derivative of z with respect to my bias is nothing but it's 1. So we computed this, and we also computed this and this. So we got all the 4 gradients. Now let us see how these are coming. So simply my derivative of loss with respect to w will be first derivative of loss with respect to y hat, which we found and came out as this, times the derivative of y hat with respect to z, which we got as this, times the derivative of z with respect to w, which we got as this. Alright, and similarly let's find the del L with respect to del B. So again it's nothing but the derivative of loss with respect to y hat, which is this one, like the same as this, times the derivative of y hat with respect to z, which is this only, so y hat 1 minus y hat, times the derivative of z with respect to b, which is nothing but 1. So you can clearly see that this and this gets cancelled and this gets cancelled. So what we are left with over here is this y hat minus y times x, and over here it's y hat minus y times 1. So it's basically this. So this is how we compute the derivative of loss with respect to weights and the derivative of loss with respect to my bias. And once we got it, we basically go to our 4th step, which is the parameters update. So here we use the gradient descent logic and we update our weights and biases. So weight is equals to weight minus eta times the derivative of loss with respect to weight. Similarly, bias is equals to bias minus eta times derivative of loss with respect to bias. So this is this and this is this. And that is how we update the parameters of our neural network in a way that my y hat, it becomes as correct as my y, so that my loss, it goes on minimizing. And that's how our neural network, it actually learns, and that's how it gets smarter over time, right? So that is the whole process of backpropagation. and I intentionally went in depth so that you guys have a clear understanding of what is happening under the hood. Alright, so now that we have understood the whole neural network process, let's code it manually so that we understand better. So this is the same collab where we have done our gradient computations, and here is my neural network coding. So first I've created my 4 tensors. First one is my x, which is my input. Second one is my y, which is the actual output. So I've told that here I'm considering the binary classification problem. So that's why my y over here is 1. And then we have 2 tensors which represent our weights and our biases. So our weights are 1 initialized, that's why it has 1. And my bias is 0 initialized, that's why it has a value of 0. Alright, and this is my binary cross entropy loss. So I've coded this loss function which takes my prediction, which is my y hat, and takes my target, which is my y. So it takes it and it calculates the minus y log of y hat minus 1 minus y times log of 1 minus y hat. So that's the formula of BC which I've shown earlier, and this is the code for it. So if you remember, first the process starts with the forward pass where we calculate our z and then we calculate our y hat, which is the prediction. Alright, so what is z? Z is w times x plus b. That is what we are doing over here in this line, which is the weighted sum also. And once we got this z, we calculate our y hat by passing this z to our sigmoid function, which basically squeezes z to a number which falls in the range of 0 to 1. So that's the simple y hat calculation or the y pred. So this is the prediction. Next we calculate the loss using this binary cross entropy function that I've created over here. So here we pass our y pred, which is y hat, and the y, which is the actual output. And in return I got the loss. And here I'm printing the loss. So this was the first step, forward pass. The second step was loss computation. And the third step was computing the gradients of loss with respect to weights and with respect to biases. So that we are doing over here. So first, as you can see, my derivation of loss with respect to weight is nothing but derivation of loss with respect to y hat times derivative of y hat with respect to z times the derivative of z with respect to weights. Similarly, my derivative of loss with respect to bias is nothing but derivative of loss with respect to my y hat times derivative of y hat with respect to my z times derivative of z with respect to my bias, right? And here we expand these terms. So as you remember, I told that we have to calculate 4 gradients. So first we have to calculate this, which is a derivative of loss with respect to y hat. So this is the code for it. So it is y hat minus y divided by y hat times 1 minus y hat. And I've shown you how this came. So I guess this should not be a black box for you. And then we calculate this derivative, which is derivative of y hat with respect to z. So it's simply y hat times 1 minus y hat. And lastly, we calculate this and this, which is the derivative of z with respect to w, which is nothing but x, and derivative of z with respect to bias, which is nothing but 1. So here are our 4 gradients that we calculated, and here is my derivative of loss with respect to weight and derivative of loss with respect to bias. So we calculate this, and here I am printing it. So this was my loss, and these are my gradient of loss with respect to weight, which is this, and this is my derivative of loss with respect to bias, which is this. So that's it. And because we don't have a fully fledged neural network, I'm not showing the 4th step, which is updating the parameters. But I hope the first 3 points are very much clear. And that is what I actually wanted to demonstrate. So yeah, that's it. Alright guys, so now that we have a clear understanding of what gradients are and how a neural network actually gets trained, I think it's the perfect time to start learning Autograd. So guys, it's important to note that our neural network, they're not just one layer model or just one perceptron model. They are huge neural networks with millions of layers and probably trillions and billions of parameters. And due to that, there will be tons of gradients involved. And if we sit down and compute all these gradients to train our neural network, probably it would take ages or generations to train just one neural network, right? And on top of that, it will be very error prone, impractical, and honestly very infeasible. So how do we compute all these gradients and how do we actually train this neural network? And that's exactly where Autograd comes in. So you can think of Autograd as this maths PhD guy whose task is to manually compute all the gradients which are involved in the training of this neural network so that we never have to manually compute any gradient, and it makes the whole training process much more fast and much more efficient. So you remember those gradients which we required in backpropagation, like the derivation of loss with respect to weights, derivation of loss with respect to all the biases. Like Autograd handles all these gradients automatically under the hood, and it does is very fast and very accurately, and that's why it makes the whole training process much more beautiful. And also it's important to note that our Autograd, it maintains a dynamic computation graph so that every time we perform a new tensor based operation, it gets appended to this computation graph. So that whenever we require any gradient, it traverses the graph backwards and computes the gradient automatically for us. So without Autograd, training a neural network would probably be a nightmare, whereas with Autograd, it is much more beautiful, efficient, fast, and accurate. And that's the beauty of Autograd, PyTorch's inbuilt automatic differentiation engine. Alright guys, now let's solve the three gradient problems which we saw at the very first using Autograd so that you understand how Autograd is actually computing these gradients automatically. So the very first question was this: y equals to 3x square, and we have to find the derivative of y with respect to x. And we passed x as 5. So with Autograd, this is how it is done. So we first create a tensor with a value of 5, which is my x, y5. The reason it is 5 over here is because here I've passed it 5, right? So whatever input I am passing, that is what you have to put it over here, and you have to make this requires grad is equals to true. Otherwise, Autograd won't be able to compute these gradients automatically. So first you have to create this x tensor with this value or any value, but because I passed it 5 over here, I'm using 5, and you have to make requires grad is equals to true. Next, you simply write the equation which was y equals to 3x square. So this is what? This is y equals to 3x square. And then what you simply do is you just do y dot backward, alright, and then you do x dot grad, so that you get this tensor which is 30. So see, first you do this, you create your input tensor, then you create the y tensor which is this equation, then you basically do y dot backward, which traverses the computation graph backwards and computes all the gradients automatically. And lastly, you type x dot gradient so that you see what is this gradient of x which has been calculated in this step. Alright, so whenever you do x dot grad, it returns this tensor so that you can see what is this gradient of y with respect to x. So it returned a tensor with the value of 30, and that is what we got over here. Now the next question is this: y is equals to sine of 10x square and z equals to 10y. So in the same way, we first create our x tensor with like this with a value of 5, because there also have passed 5, as my input. So first you do this and make sure that you do the requires grad is equals true. Next we do y is equals to sine of 10x square. So we simply write this equation and then we write z equals to 10y, meaning we simply write this equation. That's simple, right? Next what we do is we do this. So we have to calculate this. So simply you have to do z dot backwards because x, y, z and z is at my last. So you do z dot backwards so that it traverses the computation graph in a backwards manner and computes the gradients automatically. So as you can see, we did z dot backward, and then in order to see the tensor or in order to see the gradient, you do x dot grad and you got this value 240.98, and this is the same as this 240.98. And lastly, the same problem you solve in a similar manner. You first create your x and then you write these equations x, y, z and u, and lastly you do u dot backwards so that it traverses the computation graph backwards and computes the gradients automatically. And finally you write x dot grad so that you can see what is the gradient. And as you can see, we got the value of 158.75, which is again the same as this 158.75. So here we just used Autograd instead of writing manual functions for our derivatives. So first we had to create our input tensor, then we coded our equations, and then we simply called our backwards function which traversed the graph backwards and computes those gradients automatically. And lastly we did dot grad so that we can see the gradient value, because the dot grad, it returns a tensor where my gradient value is stored, and that is what you are able to see. So I think that was very simple. Now if you remember, we also coded this neural network manually right earlier. Now let's see how we can make this easier using Autograd. So this is how it works. So at first we created our x tensor or our input tensor. Then we create our y, which is the actual output. And then we create the w tensor and the b tensor, which is the weights and biases. But please make note over here that here we have to do requires grad is equals true in both weight and bias. Why in weight and bias? Because we want to find the gradient with respect to weight and bias, right? In this equation we did requires grad on x. Why? Because we want to find the gradient with respect to x. So whatever you want to find with respect to, you just have to make its required grad as true. Simply here we wanted to find the gradient with respect to x. That's why we have to make this requires grad equals to true on x. So similarly over here we want to find the gradient with respect to our weights and bias. That's why whenever we create our weights and bias tensor, we simply do requires grad is equals true. That enables Autograd to compute gradients with respect to weights and bias. So that is simple, I guess. Next we do the forward pass. So z is equals to w times x plus b. And then we do the y hat, which is the sigmoid of z. Then we compute our loss, which is the BCE of y hat and y. So we got this value. And once we compute the loss, we simply do loss dot backwards so that it traverses the graph backwards and computes the gradients of loss with respect to our weights and biases. And simply we can access those gradients using w.grad and b.grad. So this w.grad is basically this gradient of loss with respect to my weight, which is this one, and b.grad is simply the gradient of loss with respect to my bias, which is this one. So if you tally over here, gradient of loss with respect to weight is minus 2.94. It's the same over here, right? And the derivative of loss with respect to bias, it's minus 2.26, which is the same as here. So we avoided all this manual coding. We simply did this, and then we called the loss dot backwards, and then we simply got the gradients using w.grad and b.grad. So we avoided all this manual coding. Yeah, see, we calculated the loss, we did loss dot backwards, and simply we did w.grad and b.grad. And that is the beauty of Autograd, guys. Alright guys, so before going, we have one last concept which is clearing out gradients, which is very important. Whenever we call the dot backwards method, PyTorch actually accumulates those gradients instead of updating it or replacing it by the new one. So that means that during the backpropagation algorithm, whenever you call the dot backwards method, the gradients they get accumulated instead of being updated or replaced by the new one. And that's why we have to clear these gradients before the next update so that those gradients don't get accumulated. Instead, we are resetting their values to 0, which ensures that every new training step is actually starting with fresh and new gradients, which are the accurate representation, so that our model learns correctly and the training is stable. And by chance, if you forget clearing the gradients during training, then those gradients will get stacked on top of each other and the training will get hampered because that is not the true representation of your actual gradients, right? So that's why your training will be unstable and a model will perform terrible. So let's review the problem in code. So this is our x tensor having a value of 5. So this is the problem one which we solved and it has the required grad as true. Next I have y equals to 3x square. Now I'll do y dot backwards and I'll do x dot grad. So simply it gives 30, which makes sense. But if I again run these three cells like this line 43, 44 and 45, technically it should again come 30 only, right? But as I told, PyTorch, it accumulates these gradients. So if I run this and this, you see, it accumulated these gradients instead of replacing it. So practically it should come 30 over here, but it's coming 60. Why? Because it has accumulated. Now if I again run these cells, it's 90. If I again run, it will come 120. Right? So that is the problem of gradient accumulation. Now let's look at how to clear gradients. So I'm running this again. And you can see we got x dot grad as 30. So the first solution is, after we have calculated the gradient, like after we did this and this, after we got the value, we basically will update the x tensor, like this tensor, and will make its requires grad as false by this. So what will happen is, if we again try to run this y dot backwards and x dot grad, it will throw us an error, right? Because it will say that the elements 0 of tensor this does not require grad because we simply did this. So what we did is we first actually executed this, and once we got the gradient, we are updating the x tensor and we are making its required grad property as false, so that next time if we again calculate this gradient, it will throw us an error because our required grad is false. Simple. The next solution is 0 out. So here I have my x tensor as requires grad as true. This is my y, and I do y dot backwards and x dot grad, so it gives my 30. Now after I did this, I can simply run this. So x dot grad, like this one, x dot grad dot 0 underscore, so that it will take this tensor and it will zero this out. So if I run this, it gives me 0. So now if I again run this, you can see it's now 30. It's not giving me 60. But now if I again do this, it will give me 60. And if I again do this, it will give me 90. But after this, if I do x.grad.0 out, it will make it 0. So that if we do this, it will give me as 30. So the idea is we first execute these lines and then we do this so that we zero it out. Right? So we make the values as 0 so that if we're accumulating, we're getting the original value itself. So this is the second solution. The third solution is detach. So at first we create our extension and our y, and we do y dot backward and x dot gradient. Now after you got this, you basically do this. X equals to x dot detach, which removes it from the computation graph. So now if you again do this, y equals to 3x square, and you again try to run this, you'll basically get an error. So this solution 3, which is of detach, and the solution 1 of requires grad is pretty much same, because they both are removing my x tensor from the computation graph. So this is how it works. We create our x tensor, then we write our y expression, then we do y dot backward and x dot gradient so that we get the gradient with respect to x. And once we got it, we do this, which removes x from the computation graph. So that next time if we again run this, and then if we again try to calculate the gradient, it will throw us an error. And lastly, we have the torch.noGrad method. So here we first create our x tensor with requires grad as true, and then we create this block with torch.noGrad, and inside this if we write our y expression and we do y dot backward and print the x dot grad, basically it will throw us an error, because inside this block if we execute anything, it's like saying x has requires grad as false, right? So inside this block you can say that x has its requires grad as false, right? So that is why these lines will throw us an error, because inside this my x is having a requires grad as false. Yep, you see this. But in neural networks and in training neural networks, the solution which we use is this one, zero out. So at first we do the forward pass and we calculate the loss, then we zero out the gradients, and then we calculate the gradients using the loss dot backwards, and then we update our parameters. And that's the most optimal workflow that we follow in every neural network training. So I hope the whole concept of clearing gradients is very much clear now. Alright guys, so that's Autograd simplified for you all. I've linked down the code slides and also the notebook that we coded in the description below. And I've also given an exercise on Autograds. So please make sure that you check them out and solve it so that your concepts get much more crystal clear. And in the next lecture, we'll dive into neural networks and build our first neural network inside PyTorch from scratch. So it will be packed with lots of coding and practical implementations. So take a break and I'll see you in the next one.